The topic for today's lecture is spatial derivative of tensors, the del operator. In Cartesian coordinate system, we define a vector operator, or you can call it as a tensor operator, which is written here. E1 del x1 plus E2 del x2 plus E3 del x3. So what I am calling del x1, del x2 and del x3, they are actually the partial derivatives of whatever function on which this operator will act with respect to x1 or x2 or x3. Recall that the partial derivative with respect to x1 of a function is defined in this manner, being shown here. So if I have a function which depends on, say, 4 independent variables, x1, x2, x3 and t, which may represent time, then del f del x1, or the partial derivative with respect to x1, is defined in this manner. You will observe that in the numerator I have values of the function f, two values of the function f. First value is of course at the reference point x1, x2, x3 time t, but the second value is at x1 plus delta x1, while other independent variables being held constant. So this is what we mean by partial derivative of f with respect to x1, and I will refer to this quantity as del f del x1 sometimes. Now the del operator can act on tensors in several different ways. We can have what is called the gradient of a tensor t, which symbolically we denote as what I have here. When you take gradient of a tensor t, which is having its order as small t, we will see that the order of the resulting tensor becomes t plus 1. And this operation can be done. Gradient of a tensor is defined for all tensors starting with scalars themselves. The second operation is what we call as the divergence of a tensor, denoted as del dot t. So actually there is a dot operation taking place between the del operator and that tensor. This operation will result into a tensor of order t minus 1. And for this operation to be viable, the original tensor t should be at least a vector. The third way in which the del operator can interact with the tensor is called the Laplacian of a tensor t, and that involves first letting the del operator dot with itself, and it becomes another operator, and then that operator acts on my tensor t. The resulting tensor, that is the Laplacian of this tensor t, will also have the same order as the original tensor, which is t. And again, Laplacian is also, it's viable to take Laplacian of tensor of any order. There are two more items that we will require. There are two more operations that we will require in our fluid mechanics course. The next one is the advection operator, in which we first take a dot product between a vector v. So v is a vector here. We take a dot product between the vector v and the del operator, and then it becomes another operator, which we call as the advection operator. And this operator can act on any other tensor. And when it acts on any other tensor, the resulting tensor will have the same order as the original tensor. The fifth way in which del can interact with a tensor is, for our relevance, is curl of a vector. So this kind of interaction of del operator is always with a vector. So that operation is actually involving a cross product between the del operator on one side and the velocity and a vector v on the other side. The resulting tensor is also a vector, and as I mentioned earlier, for this operation to be viable, v has to be a vector. Now let's look at details of these operations, and we are interested in simplifying the expression of these operations as much as possible using our Cartesian coordinate system. So let's start with the gradient of a tensor. And for illustration purpose, I'm going to take t as a vector. But as I said earlier, this operation gradient, the gradient operation is actually viable for tensors of all order. For illustration, I am taking that tensor t to be a vector. So using Cartesian coordinate system, I can express del t, the gradient of tensor t, as what I have written here, where I have first expressed the del operator in terms of its in Cartesian coordinate system, and then I'm writing the v operator, v vector, as v1 e1, v2 e2, and v3 e3. Now, with 3 terms coming from the del operator and another 3 terms coming from this vector, potentially we have 9 terms. When you expand, when you pursue the full expansion on the right hand side, you will get 9 terms. Right? E1 del x1 acting on v1 e1, it is giving me the first term here. E2 del x2 acting on v1 e1, giving me the second term here. E3 del x3 acting on v1 e1, giving me the third term here. Similarly, when these 3 will act on v2 e2, we get 3 more terms. And finally, when E3 del x3 acts on v3 e3, you get 3 more terms. I have not written all of them here, but you should be able to write. Now let's focus our attention to the first of the 9 terms here, which is E1 del x1, v1 e1 vector, v1 e1. First, as the first step, I will use the product rule of differentiation, because del x1 is acting on v1 e1. You treat v1 e1 as product and allow this del x1 to be acting on each one of them successively, like what I have here. But then I realized that the unit vectors of the Cartesian coordinate system, they do not change when you change x1 or x2 or x3 or even time. And thus, del e1 del x1 can be set to 0. And this is not only true for del e1 del x1. Spatial derivative of any unit vector with respect to any spatial variable for a Cartesian coordinate system will be 0 all the time. Thus, we get only one surviving term, which is the first one, e1 del v1 del x1 e1, which I am writing here as e1 e1 del v1 del x1. Now, performing similar steps for the other 8 terms here, you can get additional 8 survivors, all of which I have listed here. Once you have this, you can actually recognize the pattern, how indices are changing across these 9 terms, and write that in more compact form as del vj del xi eij. Mind you, here the index of the first or the index of the left unit vector of the dyad has to match with the index of the spatial derivative. If that is what it should be, you cannot alter it. If you alter it, it will not remain del v, it will become something else. So this, you need to pay attention to this, and this is actually emerging from what you see explicitly in these 9 terms. You see first index matching, here matching, and so on. Now this tensor that we just arrived at, it is a second order tensor because it involves EI-EJ combination here. One may ask this question, what is the 1/2th component of a velocity gradient tensor? And that will turn out to be del V2 del x1, not del V1 del x2. So the 1/2th component of this tensor will be the coefficient of E1, E2 dyad, and that is del V2 del x1. In general, one may ask this question, what is the ijth component of the velocity gradient tensor? That should turn out to be del Vj del xi and not del Vi del xj. So in this manner, actually, you can get gradient of tensor of any order. You just have to follow these steps, what I have shown here. Use this product rule of differentiation wherever required. Set such derivatives as 0 when you are using Cartesian coordinate system, and you will be able to arrive at the corresponding expression for a tensor of higher order as well. Let's move to the divergence operation. And again, I'm going to take an example, even though divergence of a tensor is viable for all tensors starting with vectors. I am going to use a second order tensor here for illustration. So del dot t, I am interested in finding the expression of this in Cartesian coordinate system. I write the expression of del in the Cartesian coordinate system like before. I put a dot product and then I write the full expression for the t tensor using dyads as it is required because tensor is of order 2 in this manner. Now this will result into 27 dot operations, right? Because first E1 del x1 will act on the full tensor that I have written explicitly all terms in the first row here. Then E2 del x2 will act on the entire tensor that will appear here. I have not written all the terms, but if one wants, one can complete this, fill this blank space. Then E3 del x3 will again act on the full tensor, and that will appear as the third row in this expression. Now let's focus our attention on the first dot operation of the first row, and that is E1 del x1 dotting with T11 E1 E1. Right? Now this del x1 operation can be done first, letting the dot operation to be done after the del x1 operation has been done on the whatever is coming from this tensor. So this dot waits while the del x1 operator goes inside. Again, potentially there are 3 terms inside it if you apply the product rule of differentiation. But then again, what will happen? 2 of these terms will not survive because they involve the spatial derivatives of unit vectors, which are 0. The only surviving term will be what I have here. Once you have taken care of the the partial derivative operation, then the dot operation can be performed. And for that, the rule is the same as before. The rightmost unit vector from the left tensor is going to dot with the leftmost unit vector from the right tensor. In this case, E1 is going to dot with E1, and you finally get this surviving term del T11 del x1 E1. If you go to the second term here, let it dot with E1 del x1, you can show that the only surviving term will be del T12 del x1 E2. Then you go to the third term here, the only surviving term after this spatial derivative and the dot operation has been done, you will get del T13 del x1 E3. Beyond these 3 terms in the first row, you will not get any survivors. Why will I not get any survivor? Because let's consider the first of these remaining 5 terms. You have E1 del x1 dotting with T21 into E1, right? So you take derivative of this. The derivative operator will go and sit with T21, and then E2 unit vector coming from the right hand side will be exposed to the dot product, but that is going to dot with E1 coming from the left hand side, and that is going to be 0. For similar reason, all the other 4 terms will also turn out to be 0 in the first row of terms. So we are out of the 9 possible terms here, only 3 are surviving. When you go to the next row of terms here, again you will observe there are potentially 9 terms, 9 dot products, only 3 will survive, and similarly from the last row only 3 will survive, and in total you will have 9 survivors. I have written those 9 survivors row wise here on this slide. Now these 3 terms I actually showed you how they are turning out to be the survivors. For the second row, of course, one way to find the survivors is to perform all these steps for the second row of terms as well. How that can be done, but there is another way in which you can still get the 3 terms, and that is by recognizing the pattern of indices in the first group of survivors. See here, the first 3 survivors coming from the 3 survivors coming from the first row of terms follow this pattern. What is this pattern? The second index of t matches with the index of the unit vector. The first index of t matches with the index of the spatial derivative. See that? Isn't this enough for me to write the second survivors from the second row? Yes, it seems it is sufficient. So I will have E1, E2, E3. I will let the index of the unit vectors match with the second indices of the t of various t's here, whereas the first index of t should match with the spatial derivative. And in all these terms, the spatial derivative should be with respect to x2 as it was with respect to x1 here. So in that way, you can generate those surviving terms from the second row. Following the same steps, you can actually get the survivors from the third row as well. And once you have these 9 surviving terms in front of you, then you can recognize the pattern in which indices are changing, and you should be able to write del dot t in more compact form using the sigma notation as del t I j del x I e j summation going over I and j. Again, the same question I would like to ask: what is the order of the resulting tensor? And that I'm going to infer by how many unit vectors are standing there, whether it is just a lone unit vector, or is it appearing, or is there a dyad appearing, or is there a higher order dyad appearing. I see only lone unit vector standing here. It means that the resulting tensor has order 1, which is 1 less than the original tensor. That's what I wrote on the very first slide. Right. The next item to be discussed is the Laplacian of a tensor, and now I will illustrate this idea of Laplacian in Cartesian coordinate system using a vector itself, using the tensor to be using taking the example of a vector. So this Laplacian operator has to act on a vector. But then the interesting thing about the Laplacian operator is that first 2 del operators should dot with each other, and whatever is the resulting operator, that will act on the velocity vector. So the story about the velocity vector will come later. Let us first simplify the expression as much as possible for this operation between 2 del operators themselves. So I have written this del operator, first del operator, second del operator, taking a dot product, and you will get 9 potential terms, right? E1 del x1 acting on E1 del x1, E1 del x1 acting on E2 del x2, E1 del x1 acting on E3 del x3. That is the first row of terms here. Similarly, when E2 del x2 acts on the 3 terms coming from the second del operator, you will get another 3 terms, and finally another 3 terms when E3 del x3 gets its turn and gets a chance to act on the 3 terms coming from the second del operator. right? So there are 9 terms in total. Let's focus on the first one here. We have E1 del del x1 acting on E1 del del x1. Now again, applying product rule of differentiation, you can say that it will have, we will first get 2 terms what are written in red color here, E1 dotting with del E1 del x1 and del del x1 standing by, and then another term E1 dotting with E1 with del del x1 having been acted upon by del del x1 itself, and that we can write as del square del x1 square. Right? So del square del x1 square is just another way of writing 2 successive derivatives with respect to x1. For the same reason as before, that a unit vector of a Cartesian coordinate system does not change with the spatial coordinate. First term will go away. You will be left with the second term, and in the second term there is a dot product between E1 and E1 that gives you unity. So the only surviving term is del square del x1 square. We go to the second term. Again, you can expand it if you wish in this way using product rule of differentiation. But then, and out of these 2 terms you get from product rule of differentiation, the first term will go to 0 because unit vector does not change. But the second term will also go to 0 because now in the second term, E1 is having a dot product with E2. That takes it away. If you go to the third term here, if you insist, you can write 2 terms again out of it. First will be 0 because E3 doesn't change with x1, and then the second term will also be 0 because there a dot product is happening between 2 different unit vectors, E1 and E3. So that will also go. So in summary, the first row of terms has only one survivor, and that is del square del x1 square. Now if you continue working like this on the second row of terms, you will get again one survivor. If you continue working on the third row of terms here, again you will see that here there will be only one survivor. You can find those survivors explicitly by writing all the terms. Alternatively, looking at the pattern of indices in the surviving term of the first row, you can possibly write the survivors of the second and the third rows as well. So the first row has the survivor second derivative with x1. So I would go ahead and conclude that the survivor from the second row will be second derivative with respect to x2, and the third row will have the survivor second derivative with x3. So that is the net effect of del dot del in Cartesian coordinate system. Now once we have arrived at what the net effect of del dot del is, we have to make it act on V now. Now you can write V as V1 E1, V2 E2 and V3 E3, and you can work out all the terms. And those terms can finally be written as sum total of 9 terms in compact manner as I have shown here. This can be verified. I have not written all the steps, but one can work it out completely and arrive at this arrive at this final form. What is the order of the resulting tensor when you took Laplacian of a vector? It's turning out to be a vector. And that is again in line with what I said on my previous, what I had on my first slide. When you take Laplacian of a tensor, the order does not change. The resulting tensor has the same order as the original tensor had. Now let's talk about the advection operator. So V dot del is the advection operator where V is a vector. Now this operator can act on tensor of any order. The resulting tensor is also will have the same order as the original tensor. In Cartesian coordinate system, I write V as V1 E1, V2 E2 and V3 E3. I have to take the dot product, take a dot product with the del operator itself. I have not shown all the steps. Potentially you will have when you expand it fully, you will have first 9 terms, and then you can simplify that using product rule of differentiation and then realizing that even E2, E3 will not change with spatial coordinates and so on. Eventually, you should get three surviving terms: V1 del x1, V plus V2 del x2 plus V3 del x3, which in compact form can be written as Vj del xj summation. Now, this V dot del operator can act on any tensor of any order. But suppose there is a situation in which V dot del acts on V itself, because V after all is a vector, so it qualifies to be acted upon by V dot del like other tensors. You can treat this as an exercise. You should be able to show that when V dot del, the advection operator, acts on V, you get this expression, most simplified form in Cartesian coordinate system: Vj del Vi del xj Vi. Next, we go to what we call the curl of a vector, and the curl of a vector is the cross product of the del operator with that vector itself. So I write del as in Cartesian coordinate system as before. I take a cross product with the a vector, which is being written again in Cartesian coordinate system. You use your usual relationships, E1 cross E2 going to E3 and so on, and cross product between the same vector, E1 cross E1 will go to 0, etc. And the fact that the unit vectors of a Cartesian coordinate system do not change with spatial coordinates. You should be able to get this simplified form, what I have here. While dealing with the governing equations of fluid motion, sometimes we are required to express various tensors in not only in the Cartesian coordinate system, which we have seen earlier, but also in other coordinate systems. So now we are going to see how we express various tensors in a cylindrical polar coordinate system. So first, let us review what a cylindrical polar coordinate system is. To define a cylindrical polar coordinate system, actually in the background, we do need a Cartesian coordinate system. So in this figure, you can see I have a Cartesian coordinate system with origin O and unit vectors, and its unit vectors as E1, E2, and E3. And let it be frame embedded. Frame embedded means the reference frame in context that we have. This Cartesian coordinate system is fixed to that reference frame. Now let P be an arbitrary point of interest, and in the Cartesian coordinate system, P will have coordinates x1, x2, and x3. But in the cylindrical polar coordinate system, its coordinates will be different. So how do we define the coordinates of the point in our new coordinate system? So PO is this displacement vector or position vector of point P. PO is the position vector of point P measured from my origin O. And let me project this position vector on the plane of x1, E1 and x2, E2. And when I project it, the point where the corresponding point, the point corresponding to P on this plane x1, E1, x2, E2 is P prime. All right. Now, theta is the angle that this vector P prime O is making with the x1, E1 axis. In the sense, positive in the sense shown in the diagram. Coordinates of point PR in cylindrical polar coordinate system are theta and z. So theta is an angle, whereas r and z represent some distance, some length. R is actually the magnitude of this projected vector P prime O, and by definition it can never be negative. So that is the first coordinate in the cylindrical polar coordinate system. R is defined in this way. The third coordinate system, Z, is actually the perpendicular distance of P measured from x1, e1, x2, e2 plane. In other words, it is actually the distance P prime P, but the sign it has, there is a sign also associated with Z. So if P is on along if P is along plus E3 direction, then it will have a positive sign. If it is lying on the negative E3 side, it will have a negative sign. So Z in that way can take any positive, negative, or zero value. So in this way, R, theta, and Z are defined for our cylindrical polar coordinate systems. We also need unit vectors of this new coordinate system. So the unit vectors of a cylindrical polar coordinate system are ER, E theta, and EZ. How are they defined? ER is actually along this vector P prime O. It is a unit vector and its direction is decided by the direction of this vector P prime O. E theta is perpendicular to ER and it lies in the plane of x1, e1, x2, e2, and its direction is decided by, it is oriented in the direction in which theta is increasing. And Ez is actually identical to the E3 unit vector of my background Cartesian coordinate system. Right. Now, the way we define the unit vectors in the cylindrical polar coordinate system, some of these unit vectors may change if you change theta. In other words, what I am saying, if you take partial derivative of say ER with theta, as theta changes, the direction of ER changes. So this partial derivative is not zero. So recall in our Cartesian coordinate system, spatial derivatives of all unit vectors, spatial, when I say spatial derivatives, I mean derivatives with respect to x1, x2, and x3 of e1, e2, and e3 were all zero. Here, the spatial derivatives of the unit vectors of the cylindrical polar coordinate system, all derivatives with respect to at least theta, the second coordinate, is not zero. So del ER del theta is actually equal to E theta, and del E theta del theta is equal to minus ER. Whereas other spatial derivatives of the unit vectors, I have presented all those derivatives in a tabular manner, which is visually more appealing here. So you see there are 9 possible derivatives that we can have involving unit vectors and the spatial coordinates of the cylindrical polar coordinate system. Out of these 9, I have one non-zero here and the other non-zero is here. Others are still zero. So we have to keep this in mind, especially when you are trying to find expression for expressions like gradient of a tensor in cylindrical polar coordinate system or divergence of a tensor in cylindrical polar coordinate system. So there we have to be careful that these unit vectors at least will have non-zero spatial derivatives. Now, if I have an arbitrary vector A and I want to express that in cylindrical polar coordinate system, how would I express that? I would write that as AR ER plus A theta E theta plus AZ EZ, where AR, A theta, and AZ are components of A along ER, E theta, and EZ respectively. Note that the same vector can be represented in any coordinate system. For example, if I go back to my background Cartesian coordinate system, A would have been expressed as A1 E1 plus A2 E2 plus A3 E3. Now that whole thing is actually A, and that that A is again equal to your full expression of the tensor of the vector in the Cartesian cylindrical polar coordinate system as well. However, in general, A1, A2, A3 and AR and A theta and AZ will be all different numbers. But the vector A remains the same. That is what should be kept in mind. The vector A itself is invariant. Now let's talk about a second order tensor. If I intend to express a second order tensor in cylindrical polar coordinate system, how will it look like? Now you recall that for when we were using a Cartesian coordinate system for our expression of a second order tensor, we constructed dyads with E1, E1, E2 and E3, and then we had coefficients of T, Tij, and then we summed it over, sum that over the full range of I and j, right? Now, when using cylindrical polar coordinate system, accordingly we will have to create dyads comprising of the unit vectors of the cylindrical polar coordinate system. So you see, I have now created dyads ER, ER theta, ER Ez, right? E theta ER, E theta, and so on, all the way to Ez. So I do have 9 dyads now, and the coefficients of those 9 dyads will be the components of the second order tensor in my cylindrical polar coordinate system. And those components I am writing as TRR, TR theta. Here the subscript R theta means where order matters. TR theta means it is denoting the component of the tensor along the dyad ER theta. Right? So in this way, a second order tensor can be expressed. Again, the tensor itself is invariant. So this sum of 9 terms here is same as the sum of 9 terms when you are using Cartesian coordinate system as your working coordinate system. And again, in general, these components here are not the same as the components here. Of course, there will be some relationships between the components here and the components in the Cartesian coordinate system, but they will not be the same.